Okay, more or less. Good. How are you? Tired? Who is tired? Raise his hand. Okay, that's good. It means that we did our job, right? So I prepared, but since you succeeded to raise your hand, you are not so tired. Okay, good. So in this last day of our meeting or of our masterclass, we have prepared a series of, let's say, not quite standard lecture, because we will go to hit items which are not necessarily studied at the accelerators. And actually, as you will see from my talk, which is dedicated mostly to the underground physics, so it's a kind of a sample of what physicists do in the laboratories which are underground. And from my colleague Fabio Sciarino, after me, you will see the quantum mechanics experimental work, which is a lot of fun and very exciting. While after the break, you will have a lecture from my colleague Matteo Martini, who will tell you something about the universe and about the search for extraterrestrial life. So you see, we choose to do this in the last day to show you that there is much more than the search with accelerators and with the standard model and whatsoever, even if always or almost always that's our starting point. You see here in the background, I'll come back, of course, because this is one of the INFN biggest realization, the underground laboratory under the Gran Sasso mountain. So we will come back to this, but before that, I'd like to start to tell you something. Actually, I integrated because some of you asked me about the neutrinos. And since underground physics, it's mostly related to its neutrino studies, even if not exclusively, I integrated in my presentation some stories about the neutrino, how it came in the physics, and why we still study it and it's still being so mysterious. You have seen already this. I'm only putting it here to underline this feature. So we have seen that the matter, it's, the normal matter to differentiate it from both from what is considered to be eventual post-standard model or out of standard model like supersymmetric matter, or even to differentiate it for whatever might be the dark matter and the dark energy. So it's well understood far beyond the level of the atom. So we have seen this, that the atom structure, the nucleus surrounded by electrons, and the structure, the mere structure of the nucleons as composed by quarks, it's very well understood. It's even, I dare say, too well understood. Because what we try to do in our accelerator is sometimes to try to make failures of the predictions of the standard model. And unfortunately, somehow, the standard model is far too successful. Because even if we go to do precision experiments like 1 part per billion, we still succeed to match the prediction of the theory with what we are measuring in the lab. Somehow this is frustrating for experimentalists. We would like to come up and to shout, I discovered neutrino faster than light, for example. Well, that example is not matching very well because it was an experimental error. However, so in the standard model, in spite of the fact that it's well understood, well known, there are still a series of mysteries. And the biggest out of it, it's the neutrino. So neutrino, we know it exists, it's there in the standard model. We have seen it. We even have seen that there are 3 types of neutrinos. 3 means that each type it's related with a decay of a particle, like, for example, the muon, which generates the muon neutrino, and so on and so forth. So they are related with specific decays and with only those types of decays. The problem here is that these neutrinos, I will show you, stepped into the physics in a very funny way. And I'll show you how. And I'll tell you why we study it in the underground laboratories, but not only, and what we hope to get. So speaking about the neutrino, this is another type of view which I hope you get already accustomed with. So the standard model picture, which was integrated recently with the discovery of this Higgs boson, which if you still have some problems to understand, don't worry. We too still have some problems to understand. And when I present you this picture with the honey, or maybe somebody of you have seen the movie of John Ellis from CERN, which used as an example the snow, the fall down from the snow and the walking in the snow or things like this. If you didn't see, just go and look John Ellis. It's still, let's say, at the level of intuition. It's not so easy to get what it is, the Higgs boson, but since, thanks to a question I got from her about the symmetries and electroweak symmetry, I think I try to give you a hint of the role of the symmetry. So Higgs, it's one of the manifestations of a symmetry which is broken inside the standard model, allowing us to have a mass and allowing us to be here. Or at least this is the today view of what we think happens in the universe. Maybe tomorrow, somehow, some of you will discover something else. But today, this is our best. And in the framework of the standard model, you know already that this is not a complete satisfactory model. If not for else, and we discussed for example, with the guy coming from Denmark, what is the quantization of the gravity? So the gravity which still doesn't speak the same language as all the other interactions. So we don't have a quantized version of the gravity, which means it cannot be fit in the standard model. What has happened lately is that people have done theories beyond the standard model, like the string theory, or like quantum loop, quantum gravity, or different versions of theory. None of them yet experimentally verified, still very valid from theoretical point of view. But we still have to understand whether there is a theory which succeeds to quantize the gravity, or by itself somehow gravity is completely different from the other forces. And speaking about the quantization, Fabio will give you a lecture about the quantum mechanics and experiments. So you will see that when I use the word quantum, which we give it almost for granted, there is still a universe down there, both from theoretical point of view and from applications point of view. So now speaking about the neutrino, which is a particle, we know it exists. So by itself, its presence there, it's not mysterious. What's mysterious is to understand its mass. Now let me tell you how the neutrino came into the game. So many years ago, almost 100 years ago, when people succeeded to measure the so-called beta decay. Beta decay means that a neutron transforms into a proton and an electron. So people succeeded to measure this electron. And when measured the electron, they succeeded to measure its energy. And when they made, let's say, the sum of the initial energy and of the final energy and put them together and checked whether this is balanced, they arrived at the conclusion that the energy is not conserved. So this was coming as a real shock in the community. Oh, we have to give up at the energy conservation. And many, even eminent physicists, were almost ready to give up at our main pillar, conservation of energy. What means this? That it means that if this would be true, that if I suddenly would disappear from in front of you, you shouldn't be surprised. After all, the energy does not conserve. So, but it was a physicist, which we will meet again later on, this man you see here, Wolfgang Pauli, a very, very strange person, who was saying, so it was a meeting in 1930, and look how funny he was. So he wrote a letter to these physicists, distinguished colleagues, who were meeting to discuss the non-conservation of the energy. And he said, I have hit upon a desperate remedy. He called it desperate remedy, to save the law of conservation of energy, namely the possibility that there exists in the nuclei electrically neutral particles that I call neutrons, lately called neutrinos, I agree that my remedy could seem incredible, but only the one who dare can win. This is a message for you as well. Unfortunately, then he ended the letter. Unfortunately, I cannot appear in person to the meeting since I'm indispensable at a ball here in Zurich, which was, of course, not true because he was not quite famous to be a good dancer. But he put forward, he dared to save the pillar, namely the conservation of the energy. He agreed to put there a particle which they were not able to see, so he saved the energy conservation, assuming that together with the electron, in order to conserve the energy, then there is something else which is emitted in the framework of the process, which he called neutron, lately called by Fermi neutrino. Fermi was the one who dealt deeply with the theory of the so-called weak decay. So he came to invent this neutrino, which was discovered many years after, actually, because it's extremely difficult to measure the neutrinos. I wanted to tell you this story because I think it's a very fascinating story. Second, because it shows to you the intimate mechanism which stays inside the physics, which a very active and lively science was, and it's still like that. So it's not something which is frozen and you have to learn it because you have to learn it. It's something you can contribute to. And now, this particle, this neutrino, which are having neutral charge, they have a mass we still don't know, they talk to us only with the weak interaction, which is so weak that if we do have, each second in our eye, billions and billions and billions of neutrinos coming from the sun, and we don't feel them. In all the span of our life, maybe 1 or 2 neutrinos interact in our body. So fortunately, because if they would interact more, we would be burned down by the neutrino from the sun. The facts from neutrino. So the main, let's say, facts are the following, that the name was invented, as I was telling you, not the particle itself, which was invented, so-called by Pauli, but later on, Enrico Fermi baptized it as neutrino. They are produced, I will show you more about where they are produced from, but they are many, many produced in the stars, our sun included, of course. You see that the number, this is the flux on square meter per second. So it's a number which is quadrillions. It's unbelievable. They interact so weakly that if they would pass through a block of solid lead with a length of 5 light years. So let's imagine we would have a lead brick 5 light years, so farther away than the Proxima Centauri star. So if we would have lead all there, only 50% of the neutrino would interact. Other half would still succeed to escape. Okay? Now, where they are produced? The sources of neutrinos, you can see here from the comparison that the biggest source of neutrino coming down on Earth is the sun. In the sun, they are produced in the nuclear interactions which keep the sun alive. So in this process of nuclear fusion, where the nuclei get together to form bigger and bigger nuclei, part of the energy is transformed in neutrino, and they are really a huge number of them. Many as well are produced in our nuclear power reactors. So of course that there some nuclear processes are occurring, and as a consequence we produce neutrinos. Present days and even in the past, there were some researchers who were doing experiments or proposed to do experiments using this type of neutrino, so to study this type of neutrino. Very few are produced from the interaction of the cosmic rays. Cosmic rays means mostly protons coming from the universe, and part of them are produced from nuclear decay of the elements which are staying inside the Earth. namely the thorium and uranium inside the Earth. So these are our main neutrino sources, the biggest among which is the sun with its nuclear reactions keeping it alive. Nobel Prize, a recent Nobel Prize was given in 2002 to these two gentlemen who were doing time ago pioneering work to detect the cosmic neutrino. And before showing you some more feature about neutrinos, I want to show you a different type of lab, which is underground, but more than ground, it's under ice. So there is a laboratory at the South Pole which measures the neutrino using the pure ice which stays deep underground, at some depth. So at the South Pole, just a couple of years ago, not even a couple of years ago, was finalized the installation of the so-called ice cube laboratory, which means that they digged holes using warm, pressurized hot water. They digged holes which arrived up to almost 3 kilometers depth. And they put detectors in some lines, thousands of them, starting from 1.4 up to 2.8 kilometers. They put this sort of eyes, let's call them eyes, individual detectors, in order to measure the very teeny signal which is generated when a neutrino hits inside the ice, and some of them, very few actually, interact with the nuclei from the ice. So the ice, by that depth, it's very pure, and we can see very clean signal produced by the neutrino in the ice. So we see the particles with the detectors, which are daughters of the interactions of the neutrino with the nuclei from the ice. And actually, it was quite, I show you some pictures. So this is, let's say, a more detailed view of these chains of detectors. This is work of the team. They could only work in the summer South Pole, which means our winter, and conditions were not so easy. These are the water which was used to dig these deep holes, and the installation, they should work fast because otherwise the ice gets back to shrink. This is one of the tunnels with the installation of one of these eyes. This is one of the very last which was installed. People, everybody smiling, happy for the success of the installation. This is how it looks like. And here is when they were installing the chain of this kind of... What I want to tell you is that they were already rather successful since they have seen few events. They did see already many neutrinos, but among these, around some tens of them were of very, very high energy. They even baptized, I don't remember exactly the name, Earth and Benny or something like this, the two events corresponding to the highest energy of neutrino. And we can learn a lot, not only about the neutrino coming from the sun, but about possible neutrino coming from different sources in the universe. Now, what's still the matter of the neutrino? The matter is that we know that they do not weight, their weight is not zero, so they do have a mass. But we don't know how big or how small is this mass. We have some limits. For example, for the first species of neutrino, the electron neutrino, we know it's about, at most, about some 1,000 times lighter than the electron. And for a long time, the neutrino mass was believed to be exactly zero. But there are some phenomena occurred which made physicists to understand that actually they do not have zero mass. But we don't know how much it is. So which are the phenomena which made physicists to believe, to understand that their mass is not zero? One of them was the fact that many experiments, some of them underground, some of them on Earth, measuring neutrino in the last years, neutrino coming from the sun, since we have a model of the sun, we know more or less how many we should see. And this is the Monte Carlo, so this is the model we use. So we normalize what we measure to what we believe should be there. Of course that what we believe and what we measure, if the theory is right, should be 1. Now the fact is that there were some experiments which were near 1, but as you see, this is the error bar. They were not so precise experiments. When people started to do precise experiment, they have actually discovered that these experiments can be discarded because the error is too big. But what as well came as a shock was the fact that you measure about half of the neutrino that you were expecting to get. These were very shocking because you had 2 alternatives. 1, to believe that your sun model is wrong. So to believe that what you calculate as being the nuclear reaction in the sun is wrong. So, but in order to do this, this means that you wouldn't understand the nuclear physics. So people did not want to give up nuclear physics to understand the sun. The second alternative was to believe that what started as a neutrino, as an electron neutrino from the sun, because these experiments were measuring a certain type of neutrino, somehow in its path from the sun to us, lost its identity, so transformed to something else. To what else? To a different neutrino species. I know that this is not so easy to understand, but there are in physics processes in which a particle type can transform to another particle type. This process is called oscillation. In this case, it was oscillation of the neutrino, and this would have saved both the physics in the sun and, moreover, what it's measured on the Earth. But the type of process which is the oscillation of the neutrino, so transformation from one type to another type, it's possible, at least this is what we know from all the other type of processes which we have seen like that. In Daphne we see it with cones. It's possible only and only if neutrino have a mass. So this is how it came, the idea. So it's not that people succeeded to see the mass. They deduced the neutrino has to have a mass because it oscillates. It oscillates because it should have fit the solar model otherwise, and we see that this is not the case. So this means that somehow the neutrino, which starts from one type from the sun, they do arrive, only part of them, a bit higher than 50% at the Earth as original neutrino. The other part transform, oscillates, you will see here. So I point here to the neutrino. So what can happen is that the neutrino in certain conditions do transform from one type of neutrino to another type of neutrino. So it's this oscillation which could occur. Now, of course, this is a theory. Is this true? The fact that we have measured and didn't fit with the model is not good enough to say this is true. So what you have to do? You have to do a kind of direct test. Direct test means you really start with some neutrino of some type, and you really do see on another laboratory, after they fly some region, that you start with one type and you end up with another type. So you want to measure this thing that you imagine. I put here this formula only to show you, for example, this is very relevant because it's what the opera experiment in Gran Sasso is doing. So they want to see what starts from CERN. So in this case, we have a controlled beam of neutrino, of muon neutrino. And this is the probability to get, if you start with a muon neutrino, a tau neutrino. And it goes something like this, where you have a dependence on the path length and on the energy. But since we can control the beam in this case, because the beam of neutrino is generated from one of the accelerators of Geneva, of CERN, not LHC, but a pre-accelerator of LHC, you can hope to see the appearance of a tau neutrino when you know you started only with the muon neutrino. So now we move to the real underground laboratory, and I show you here why we go underground. So we go underground because on the Earth, in the laboratories on the Earth, a part of the processes you are interested in, like here in Daphne, so you create counts, whatever, you have as well a number of events generated from cosmic rays. Now, for the experiments at Daphne, or those in the most accelerators, we don't care. The rate of these events, it's much smaller than what we really measure. So we simply don't care. However, when you have to deal with very rare events, like those generated by neutrinos, but many others yet, you do care, because then the number of events which come from the universe can be much, much, much bigger than what you are interested in. And they fake your experiment. So you might be tricked by the cosmic rays when you want to see something else. So the thing you can do is to filter the particles coming from the cosmic rays. How do you filter them? Well, you should put a filter, or you can use the natural filters. Natural filters are the Earth, or the ice in the first case. Here we have a type of underground laboratory which stays under the mountain. There are others which stay in deep mines. So those which were used to extract, I don't know, salt or whatsoever, people go there and do their laboratories there. In this case, we use the tunnel, as I show you, to measure, to filter the cosmic ray and to allow to work in the so-called cosmic silence conditions. And then you can really see rare events. The Gran Sasso Laboratory stays something like 150 kilometers far away from Rome in this region, in a very nice region. This is a picture taken, it's under this mountain. Here is the external laboratory. We have as well external part of the laboratory. Here, under this mountain, in a tunnel where cars are going from L'Aquila to Teramo, in a tunnel which is about 11 kilometers long, at halfway, more or less, in this tunnel, there is the entrance in this underground laboratory, which is structured in very big holes, 3 like cathedrals, really, really big holes where huge experiments are installed, and many, many other barracks, as I will show you, where smaller experiments are installed. And all they do require conditions of cosmic silence to see extremely rare events. This is some, let's say, additional information. So it stays under 1,400 meters of rocks. The cosmic silence is characterized by the fact that you get only 1 part per million particles after the mountain. And the things which are done there are neutrino physics in first, dark matter search, so they try to check whether some dark particles succeed to arrive together with the neutrino, as well as geophysics. They have even seen earthquakes with their instruments, even if this is not the main research, of course. Some biology, how the plants grow in the lack of cosmic rays. And it looks very interesting, this one too. It looks like the cosmic ray playing a role in the fact that we were developing as creatures able to live with a certain dose of radiation. So this is the Gran Sasso Mountain. This is the external structure of the laboratory. This is once again the lab as you can see it. And this is the opera experiment. Now I go back to the neutrino, and I show you the detector, the one which unfortunately reported neutrino faster than light. I say unfortunately because that was not their main goal. And when you do that, people start to be a bit pushy towards whatever you seriously are doing. But they really did serious physics, which was their main goal, namely oscillation of neutrino. And they really did see tau neutrino when they were expecting mu neutrino. They have seen many muon neutrino as well, but they have seen that part of them do transform in tau neutrino. So the oscillation, it's true. So the detector, it's a huge detector. You see here there is a car. So huge detector because you need huge mass. Ideally, you would need a 1 cubic kilometer under ice, but you can't do that. And they measure neutrino produced at CERN with this gun of particles. The production, I don't want to insist, it's a chain of reactions which generate in the end the muon neutrino. These neutrino go underground, so they go from CERN to our lab, passing at the deepest way at 11 kilometers underground. Of course, that there is no beam transporter, so there is not a hole or a tunnel transporting the beam there. If not for else, because at 11 kilometer depth, it's extremely hot. So it's underground, it's very, very hot. And this is how it looks like. The detector, it's a sandwich of nuclear emulsions, so we really do pictures. We picture the processes generated when the neutrino comes inside the stack of lead. It interacts in the lead, and the products are seen by emulsion, nuclear emulsion, so we do pictures. And we succeeded to measure this neutrino, and we have seen few events which corresponded to the tau neutrino. There is another experiment at Gran Sasso, studying the neutrinos, which is the so-called Borexino, which does different type of study, so they don't look necessary. They can see, but not as well as OPERA. Neutrino coming from CERN, instead they see extremely well neutrino coming from the sun. So they measure, it's a huge ball of filled with scintillating liquid, seen by thousands of photomultipliers all around. So when the neutrino comes, create a light photon, and this is seen by the detectors around, and out of its characteristic, we can measure the energy of the original neutrino. And what they have done at some point, it was a very, very interesting feature. Namely, at some point, they said, why shouldn't we look, or why shouldn't we measure as well, since we can, neutrino which are not only coming from above, from the sun, but we can as well measure neutrino coming from the Earth crust, namely those generated in the decay of thorium and uranium. And by doing that, they concluded what's the missing piece of information, or let's say not so precise piece of information. The ratio between how much thorium and uranium stays in our Earth. And they deduced some ratio factor out of the measurement of neutrino, which is not only scientifically interesting, it's strategically important too. Because if we want to go on with the nuclear power reactors of the third plus or fourth generation, which is using thorium instead of uranium, we know that uranium is a strategic resource, and it will suffer sooner or later the same fate as the oil. So at some point it will get exhausted. Is it worthwhile to go to a very difficult way to build new power reactors on thorium if thorium is not in the ground? So it's a strategic information too. If we have a lot of thorium there, able to give us energy for the next 500 years, maybe it's worthwhile at least to continue the study. If we know it's not there, it's not worthwhile to spend our money like that. And it looks like in the ground it's something like 3-4 times more thorium than uranium. So would represent a desperate solution for whenever we are not able to get energy somehow else. There is another type of research which is very interesting, done in the underground laboratories, which is the search for dark matter particles. So since we don't know what dark matter is composed of, we can only, let's say, make some hints. And one of the hints, I heard somebody of you saying this word WIMPs. So weakly interactive massive particle. So one of the hypotheses, actually the most natural one, is that the dark matter is composed of particles. Why I'm saying this? Somebody might be, what else? Well, at some point it was an hypothesis that the dark matter might be composed of remnant planets or remnant rocks, matter like we are done, but since we can't see it, it could be that in the universe there are so many rocks all around, you don't see them, and they are much more than you might believe, and so on and so forth. It was actually done a search for this type of macho objects, so massive objects which are in the space. But they were not found. They were not found. So it remained the natural solution to assume that the dark matter is done of particles of some sort, either supersymmetric particle or whatsoever. And there are many experiments in Gran Sasso. You see here those related with a project which is Dama Libra, which are doing a lot of, it's not the only one, I choose this for an example, but there are many others as well, which are looking for this type of interactions of particles coming. Now don't try to read this, don't try to read, I didn't try to read it as well, I took it from colleagues, but it's far too rich in information. It will be placed on the web where you can find all the slides, and then if you wish and you have time, you can study it in detail, since indeed it's interesting, but it's difficult to explain. So what happens? The method, one of the methods you might have to study the dark matter, it's not a really direct method, but it's most like an indirect method, is that if it comes from the universe, you might assume that, that it interacts with the Earth and with the matter on Earth differently as the Earth rotates around the sun. So since the Earth rotates around the sun and we are invaded by a flux of particles of dark matter, it's differently, so the interaction rate, the number of events you might get from the interaction, it's different if the Earth goes against the dark matter, then you have more energy, so you might expect more events, that when the Earth goes more or less in the same direction, so you have less energy when the dark matter particle hits you. So you might have a different number of events produced during winter and summer, for example. Is this concept clear? So you might expect a modulation in time during the year because of energy. So like, for example, if two of us, if we walk on the different directions, when we hit, we fell down. If we walk in the same direction, when we hit, we might, okay, sorry, it's not so dramatic. This is more or less what it's supposed to happen when particles of normal matter meet particles of dark matter. In one direction of the Earth, boom, lot of energy. In the other direction of the Earth, boom, less energy. So you might have different type of rate of events. So that's what Dama was studying this kind of difference, the annual modulation. So what they actually, well, they have a very complicated, very clean detector. In this condition, the cosmic silence is fundamental. It's similar to what it is cooling the Nautilus detector to get the gravitational wave. You have seen that gravitational wave you can see because you cool down. Otherwise, there is a desperate motion, thermal motion of the normal atoms, and this completely would cover your signal, your faint signal. It's the same here. So you need to be in silence mode in order to be able to see what comes eventually as an annual modulation from the universe. And this is what they see. Do-dum, 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 do-dum. So measuring the signal which was generated, they had indeed seen this modulation. Now, why you didn't know this? Why people do not say, okay, we discovered the dark matter, it's there, it's like that and like that? Well, because what they have seen is not a direct measurement once. What they have seen is indirect measurement of an annual modulation of some signal. People are not yet fully convinced that this is due to dark matter. So nobody would say that this is not a modulation. It certainly is a modulation. Whether this is indeed generated by dark matter, it's still a matter of research. Because, of course, because the argument is so important that if this is indeed a signal due to dark matter, at least to me, it's no doubt that they would deserve the Nobel Prize Would be the very first signal of dark matter being there. Some other experiments are looking for the same modulation, and some of them did not see it. It's true that those who did not see it do not use exactly the same method as Dama. So there is still place for future research that this is indeed due to dark matter and not to some other let's say, more trivial process. Then, now I want to show you some lines about my experiment in Gran Sasso. So we have as well an experiment there doing crazy things. Of course, whomever goes in Gran Sasso does some crazy thing, dark matter, neutrino masses. We do an even crazier thing. We look for violation of one of the principles which stays at the root of stability of matter. This is the so-called Pauli exclusion principle, which states that there cannot be two electrons in an atom having the same quantum numbers. Now, this might tell you nothing, but the translation is, when you study in chemistry, the way in which the electrons are positioned against an atom, right? 2 on the 1s, 2 on the 2s, 6 on the 2p, and so on. So there are some rules in chemistry. You are aware of this, right? That rules reflect the Pauli exclusion principle. So it's a direct manifestation of the Pauli exclusion principle. You see, again, Pauli. Here you see Pauli, very fascinating by, how it's called, how? Yes, spinning top, right. So he was fascinated by the movement because he was one of the persons involved in discovering the spin of the particles. And he got a Nobel Prize for his principle. But he, as a weird person he was, in the same spirit, never satisfied, go on and the progress is there. He was saying that already in my original paper, I stressed the circumstance that I was unable to give a logical reason for the exclusion principle or deduce it for more general assumption. I had always the feeling, and I still have it today, that this is a deficiency. So the impression that the shadow of some incompleteness fall here on the bright light of success of the new quantum mechanics seems to me unavoidable. Well, this is a very general statement, but for what concerns his principle, he was somehow unhappy that he had almost to force it by hand inside the world. It's related with some symmetry again, symmetry of the wave function in this case. But however, so people were looking for deeper reasons. What we do in Gran Sasso, we established an experiment which are looking for completely crazy transition which should not occur in nature. Namely, transition of a third electron to the 1s level in copper. These are having a special signature, so if they are there, we can see them. Actually, we didn't see them, otherwise I would be in Stockholm by now, and you would have heard about. But we have established very strong upper limits for the probability that this process occur. So you see here, this is completely forbidden process in normal quantum mechanics. If we see it, it means we hit something very, very, very strange. This is our sigla, so of course it defines what we are studying. And we point towards a probability, now forget about the symbols. The only thing which is really impressive is that we are able to arrive with an upper limit of the process of the level of 10 to minus 30. Of course, the probability of violation should be small. Otherwise, the universe wouldn't be here. All the electrons would have, boom, fall down on the nuclei. So the limit should be small. So we are hitting towards this probability, and these are us. In Gran Sasso, we don't have a big hole. We have only a small barack where we don't fit all inside together inside. So some of them were smiling in front, some other were working inside the barack. And we were installing it, an apparatus where we studied these interactions of... now I show you something. You see, we use the shielding. We still need to shield, so to cover the experiment, in spite of the fact that the mountain filters cosmic rays, there is still a leftover of background of radiation, which is the radiation coming from the rocks. So radon, all whatever it's emitted from the rocks inside Gran Sasso and everywhere. Here too, there is some radiation coming from the natural decays in the environment. So you see here that even then we were doing a lot of activity in order to protect our apparatus from the background coming from the Earth. So this is how it looks like, and we were very, very, very worried. Somebody of you can tell me which is the weight of a lead brick? More or less. It's almost 15 kilos, one brick. So you take one brick, it's almost 15 kilos. So you can imagine, somebody fainted at this news. So you can imagine that after we put everything together, we were thinking if we forgot something or if something is broken, some cables got unstuck, we would kill ourselves because dismounting these tons and tons and tons, it's not a trivial matter. And we were running, now we are trying to do better and better, so to improve this sort of experiment. And I'm approaching the end. So approaching the end, you see the underground physics, it's more or less synthesized here. So of course that what we are trying is to dig into the mysteries of the universe. And among this, what I showed to you was some hints about the neutrino physics and about the dark matter physics. Of course that in an underground laboratory you can do much, much more. Actually in Gran Sasso, I didn't want to overdo, but in Gran Sasso there is a peculiar experiment. If you wish, you can look at the slides on our webpage presented at Incontri di Fisica. They might be maybe in Italian, I'm not sure, or in English. There is an experiment which is called Luna, which is studying very interesting things. Namely, they got a very, very small cyclotron, which is a type of accelerator, but which accelerates at extremely small energies, some particles, in order to study nuclear reactions at very low energy in the absence of the background, with the goal to still tune and refine the parameters which are important for nuclear reactions, which are getting on at laboratories and in the sun in a very small energy region. So we still don't understand yet everything on the processes which are going on in the sun. So I only wanted to give you an overview. There are more labs of, I jumped this slide, I want to come back right now. There are more labs of underground physics. Gran Sasso, it's of course not the only one. It's, I guess, the biggest one in the world. It's not the only one. But there are many others. Some others are still coming. This is not very recent. It's some years old. It might be that, meanwhile, situation has even changed, where you can see here the type of depth in water equivalent. So this is water equivalent, and this is the intensity of the particles coming from the cosmic rays in the world. So you see that Gran Sasso stays rather well, but there are there were, and some of them are still being built. This, I repeat, it's not extremely recent. Only to tell you that Gran Sasso is not the only one. There are some other laboratories which are being built, and some of them will certainly be built in the future. And since today, well, we are approaching the end, but, well, today it's a special day. I want to wish you a happy San Valentino, happy San Valentine's Day. So I hope you will celebrate somehow. It's the one dear to you. And I want to celebrate it with a picture taken from physics. This is coming from a lab which is doing nanostructures. So this is done in nanocarbon. This is the scale, so it's 200 microns. So they succeeded with nano particles to build this kind of symbol. And well, happy Valentine to all of you. Life is not only science, it's love as well. So I hope you will enjoy it in the afternoon. Thank you very much. Thank you very much, and